So last few problems here, home stretch. Let's finish up with all of these modeling problems here. So one particular situation, all I'm asking you to do is use your knowledge of constant differences or constant ratios and just determine which parent function would fit the model, would best model the data. So just understand that if we're trying to check to see if something is linear, we have to go to the first differences. So we'll look at all of these and find the first difference. Remember, to find these first differences, take the second number and subtract the one before it. So 375 minus 325, we went down 250. 225 minus 375, subtract those, down 150. Down 90, down 54 for the other ones. Now we know it's not linear because those numbers are not the same. So then we move on to second differences. So notice that there's 1, 2, and 3 second differences that we can find here. And once we do the second differences, notice we went up 100, then we went up 60, and then we went up 36. So that tells us it's not quadratic. Next, let's do ratios. To do the ratio, let's take the second number and let's divide it by the one before it. 375 divided by 625. We do the same thing with the other ones. So 375 divided by 625, get 0.6. Here, 0.6. Here, 0.6. Dividing all these ones in their order there, we get 0.6 every single time. So that means, since we have a constant ratio, that this parent function is exponential. Oh, the other thing I will say about this problem is that you could also do this by using the graphing calculator. Yeah, and notice here that when we did regression analysis with linear or quadratic or exponential, notice that with exponential it's the only one that gave us here an r squared of 1. So that obviously is going to be the best fit. How about this one, number 10? Determining what that n is. A couple things we do know about this. We have all the data around n. We also know that this was a quadratic model. So if it's a quadratic model, then what we can do here is run through the first differences, which would lead us here. Went up 8, up 6. We don't know what those ones were. But now, because this thing is quadratic, we can assume that the second differences will be constant. So if we find the difference right here, which is -2, we can fill that in for the rest of them. And if we fill those in for the rest of them, that helps us figure out that the first blank right here has to be going up 4. And the next one's 2, but that really isn't that crucial or critical to know that now we know that n is going to be 31. And then when it comes time to finding now the equation for it, we're going to take that data and enter it into our table. So pressing the stat and the enter button, and then going over to calculate our quadratic regression leads us to this value right down here. And remember, we can interpret all that information and throw it right into our equation just like this. Okay, so we have -x squared plus 13x minus 9. Alright, last problem here. Given this data here, let's predict the population of Lincoln Valley in the year 2012. Like I said before, I'm going to modify this here. I'm going to modify this problem, and what I'm going to ask for full credit is just give me the equation, the best equation to model this data. Okay? In order to give me the best equation to model the data, the first thing you have to do is enter the data in your calculator. So we do that. And to get a better idea of what kind of data that we're dealing with here, how about we make a stat plot out of this? So to do that, stat, enter in your data there. And then what we'll do next is we'll hit the second button and go to the y equals, which will be our stat plot. So we're going to turn that on. We already have a scatter plot. We already want us to do those things there. And let's take a look at what we have next. It'll create that scatter plot there. And oh yeah, by the way, don't forget that when you have that data entered, to press the zoom 9 button. Zoom 9 before you look at the graph. That way it will nicely fit all of that data and all those data points that we want right in there. So now the question becomes, is this linear or exponential? So to figure out if that's linear or exponential, let's go ahead and proceed in doing some regression analysis. Let's do some linear regression, and let's do some exponential regression on it. So we go back. There's our linear regression value there, 0.997. Not too bad. Look what happens when you do exponential regression, 0.9997. So this one's clearly better. Now this is where we can stop here, and now we can take apart what we have here with this exponential regression and figure out what the equation is going to be for it. So what we can do with this is, now that you have the information here and you have the best R-squared score that fits the data, now all I want you to do to write the equation is, now we can just take this A and this B that we just found here and here. So that means we have 974. Oh, don't forget your f of x or your y. I don't care if you just copy what they have there and put y. That's okay. 974.89. And then we'll multiply that times b. Kind of looks like a plus sign with my circles there. Let's erase that. Times b. And b here, that base value of our exponential function here, is 1.0. Let's call it 1.08. And let's raise that to the x. There we go. You take it this far, I'm happy. Now, how could you actually answer this question? Predict the population in the year 2012. Well, why don't we just take this data that we have right here, this 974.89 times 1.8 to the x, and let's determine what value do we actually need to raise this to predict that population in 2012. Let's go back and look at the data. If we look at the data here and look at this a little bit deeper, this is going from 2000 to 2006, right? So right here is the year 2000 when we had a 1 here. At 7, that would be 2006. So our x value, if we were looking for 2012, x value, if 2006 is an x value of 7, then 2012 would need an x value of 13. So what we're going to do is we're going to take that 13 right there, we're going to plug it right in there. So let's just raise it to the 13th power. So now we have 2349. Let's try and find the best answer. 2349. I'm missing something here. Did I write that right number there? 974. Let's check my number. 974.89. Is that the right number? Yeah, that's the right number. 1.08? 1.08. I wonder if that makes a difference. Boy, because that number's really off. Let's put that back in. Let's raise 1.08. Oops. Sometimes I wish I had a cut button, right? Oh wait, I do. I'm not going to use it here. Wow, do you see that difference? Just missing that by 1. What you're witnessing right now, if you're watching this video, is something that I had not noticed or even thought about when I was looking at this problem. Do you see how if we make just the smallest of a rounding error? Look at this, 2651, which leads us to the correct answer here, which would be 2651. It would be this one right here, right? Realize that if we made just the smallest of mistakes and had that as a 7, I'll go back to my first mistake there, putting that as a 7. We get 2349. That's all. That's like about 300 difference of about 300. 2349. Then guess which one you're picking? You're probably picking this one here, and you're getting the wrong answer. Wow. So one thing to keep in mind, boy, with a problem like this, and it's a very specific example, of course, but see how important rounding is to getting the correct answer.